Hello everyone. So in this session, we will be discussing about what is frequency response, what are the advantages of frequency response, and what are some frequency domain specifications. Okay, so let's look into that. Frequency response is defined as frequency response is defined as the steady state response of a system to a sinusoidal input, to a sinusoidal input. Okay, so when you're applying a sinusoidal input to a system, what is the output at steady state? Steady state response. Response means output as a function of time t. Okay, so that is what we mean by frequency response. Now, what's the specialty of the sinusoidal input? It is a unique in the sense that any signal can be represented by a family of sinusoids of varying amplitude and frequencies. That's the basic idea behind for your series. We know that. Okay, so any signal can be represented as a function of, as a family of sinusoidal waveforms of appropriate amplitude and frequencies. Right? Now, let us consider frequency response for an LTI system. Okay, so the input is, say, a sine waveform, okay, whose amplitude is x and frequency is omega. X sine omega t. Okay, so what will be R of S? R of S will be x times omega divided by s square plus omega square. We know that. Why? Because Laplace transform of sine omega t is omega divided by s square plus omega square. Okay, so we know R of for R of t equal to x sine omega t, our R of S Laplace transform of the input will become x into omega divided by s square plus omega square. Right? Now you consider a stable LTI system. Consider a stable LTI system, linear time invariant LTI system with the transfer function g of s. Transfer function g of s. Okay, so you have a system here like this, g of s, input is r of t, or its Laplace transform will be r of s, the output is, say, c of t or c of s. Okay, so we know transfer function is the ratio of Laplace transform of output to Laplace transform of input when all initial conditions are 0. Okay, so that is what is g of s. So we can write g of s as c of s divided by r of s, correct? Ratio of Laplace transform of output to Laplace transform of input. So I can write g of s as c of s divided by r of s. Okay, so what will be my output? C of s. Output C of s will be r of s into g of s. Okay, now we are considering a stable. Okay, what do we mean by stable transfer function? A transfer function is said to be stable if all the poles of the transfer function are in the left half of the S-plane, or all the poles are having negative real parts. Okay, here we are considering such a stable transfer function g of s. Fine. Now we know what is r of s. R of s is this, so we'll substitute it here. So your c of s will become x into omega divided by s square plus omega square into g of s. Okay, g of s is the stable transfer function. Fine. Now this can be written as x into omega divided by s plus j omega into s minus j omega. Okay, into g of s. What I did, I splitted this denominator into two factors, s plus j omega into s minus j omega. Okay. Now, how can we find the output response? What do you mean by response? Output as a function of time t. But here on the left hand side, we are having c of s. So we need to find c of t. So what will be the response? C of t. C of t will be response. C of t will be what? L inverse C of s. Okay. L inverse C of s, right? That we know. So now we have to find what is C of t. Okay. So how will you find C of t? L inverse C of s, right? Now this C of s needs to be solved because you cannot straight away find C of t from this expression, right? We have to go for partial fraction. So I will write this as a by s plus j omega plus b by s minus j omega plus. So depending upon the transfer function, there will be partial fraction terms arising out of g of s as well, right? Say for example, g of s is, for example, g of s equal to 10 by s plus 1 into s plus 2. Okay, so this will be say k1 by s plus 1 plus k2 by s plus 2. Okay, so in addition, since g of s is a transfer function which has a form similar to this thing, right? So you can write plus partial fraction terms due to g of s. Partial fraction terms due to g of s. Okay, so let me mark this as equation 1. Okay, so this is marked as equation 1. Now how will we solve for a and b? Now we need to solve for a and b. Okay, so I will show it here. So we know that x omega by s plus j omega into s minus j omega is a by s plus j omega into g of s, also there, that is missing, plus b by s minus j omega plus partial fraction terms due to g of s. Okay, so we can cross multiply both. We can multiply both the sides with the denominator. So what will you get from here? You will get x into omega into g of s equals a into s minus j omega plus b into s plus j omega plus partial fraction terms due to g of s. Okay, partial fraction terms or terms due to g of s. Okay, so from this, how can we find a? A will be nothing but x into omega into g of s divided by s minus j omega at s equal to minus j omega. How? Because if you put s equal to minus j omega, this term becomes 0, right? So all other terms here will have a product of s plus j omega into s minus j omega. So if you put s equal to minus j omega, all those terms becomes 0, right? So you can find what is your a. So you will get your a as minus x gj omega divided by 2j. Okay, wherever you find s, replace s with j omega. So here it becomes minus 2j omega, omega and omega gets cancelled, You will get your A as minus x into minus x into g of minus j omega by 2j. Similarly, how will you find B? B will be x into omega into g of s divided by s plus j omega. So now we want to solve for B. So if you want to solve for B, A part must be made equal to 0. So you have to put s equal to j omega. S equals j omega. So what will you get? X into gj omega divided by 2j. Right? Now, gj omega is a complex quantity. Correct? Gj omega is a complex quantity. And we know any complex number has some magnitude and some phase angle. So I can write my gj omega as mod gj omega, that is the magnitude, and angle gj omega, that is the angle. Okay? Or in Euler form, I can straight away write mod gj omega e raised to j phi. What is phi? Phi is nothing but angle of j omega. Okay. Similarly, what will be g of minus j omega? G of minus j omega magnitude will be, see, keep in mind 3 plus j4. What's the magnitude? 5. What's the angle? 53.13 degree. Similarly, 3 minus j4. Magnitude remains the same at 5, and the angle will be minus 53.13 degrees. So here magnitude remains the same, gj omega, and angle of g of minus j omega. Or in polar form, I can write gj omega e raised to minus j phi, where phi is angle of g minus j omega. Okay, so that means I can write, instead of g of minus j omega in A expression, I can put this expression. Okay, and instead of gj omega in B expression, I can put this. So what will you get? So you will get A as minus x into mod gj omega into e raised to minus j phi divided by 2j, and B as x into mod gj omega into e raised to j phi divided by 2j. Okay, so these A and B values I will put in equation 1. Okay, what is our left hand side? C of s. So C of s equals, I can write C of s equals, so my equation 1 implies what? C of s equals, so my A is minus x into mod gj omega into e raised to minus j phi by 2j. So A by s plus j omega plus B. What is B? X into mod gj omega into e raised to j phi by 2j whole by s minus j omega plus terms due to g of s. Terms due to g of s. Okay. Now we can take Laplace inverse transform. So now what will be the response? Response C of t will be, response means what? Output as a function of time t. So response C of t will be L inverse C of s. Okay, so what will you get? When you take L inverse of this thing, you will get minus x into mod gj omega into e raised to minus j phi by 2j. Okay, into L inverse 1 by S plus J omega. L of e raised to at. What is that? 1 divided by S minus A. And L of e raised to minus at is what? 1 by S plus A. Okay. So if you apply that, you will get this into e raised to minus omega t plus from here we will get x into mod gj omega into e raised to j phi by 2j into e raised to j is there, e raised to j is there, huh? E raised to j omega t plus response terms. Okay, response terms due to g of s or due to so response terms will be governed by the poles. Okay, due to the left half plane poles of g of s, to be more specific. Okay, now we have seen that any response consists of two parts. One is the transient part and the other one is the steady state part. So transient part is contributed by the system pole. Okay, so that means this is the transient part, and these two are the steady state components of the output. Okay, so steady state response is governed by the poles of the input function. We had already seen that. Okay, so it is in line with that. So these two terms came out because of the sinusoidal input function. Okay, now we have considered a stable LTI system. That means all the poles are in the left half of the S-plane. So as t tends to infinity, the transient part dies out to 0. Okay, and at steady state, we are left out with the steady state response. CSS will be equal to what? We are left out with only these two terms. So minus x into mod gj omega into e raised to minus of omega t plus phi divided by 2j plus x into mod gj omega into e raised to j is there, no? J is there. J omega t plus phi divided by 2j. So this becomes what? This becomes, so I can take x gj omega by 2j common. Okay, so I can write it as x into mod gj omega into what? Into e raised to j omega t plus phi minus e raised to minus j omega t plus phi divided by 2j. Okay, and what is this thing? This is nothing but sine omega t plus phi, because we know e raised to j theta. What is that? Cos theta plus j sine theta. And e raised to minus j theta. What is that? Cos theta minus j sine theta. So if you do a little bit of manipulations here, you will see that sine theta is nothing but e raised to j theta minus e raised to minus j theta divided by 2j. So I can write this as x into mod gj omega into sine omega t plus phi. Okay, so the steady state response is x into mod gj omega into sine omega t plus phi, or I can write it as c into sine omega t plus phi. So what's the output amplitude of output amplitude? Output amplitude is c, and what is that? X times mod gj omega. Okay, and what's the output angle? Phase angle phi. Phi is angle of gj omega. Okay, phi is angle of gj omega. So what does this mean? This means that for an LTI system, for a stable LTI system, the output, when you apply a sinusoidal input, the output at steady state is also sinusoidal. Okay, what was our input signal? Our input signal was x sin omega t. Okay, so output is also sinusoidal. What is the output sinusoidal frequency? It is omega, which is same as the input sinusoidal frequency, omega. But the output amplitude has been changed from, but the output amplitude is different, right? What was the input amplitude? It was x, but now the output amplitude is x times mod gg omega. Okay, so output is different from that of the input. Now, what was the input phase angle? It was 0 degree, sine of omega t plus 0. You can write it like this, sine omega t plus 0 degree, right? But what is the output phase angle? There is some phase shift phi, and that is given by the angular part of g of j omega. Okay, so that means if we know, thus by knowing the transfer function g of s, the transfer function g of s of an LTI system, the complete steady state performance, can be obtained for a sinusoidal input. Okay, so the output amplitude is determined by the transfer function magnitude, and output phase angle is governed by the transfer function phase angle. So it is very easy. Okay, so you can see here we are dealing with gj omega. Okay, we have the transfer function g of s, right? So when you are doing frequency response, we are dealing with gj omega only. Okay, this was mod gj omega angle gj omega, right? So gj omega is called sinusoidal transfer function. Gj omega is called sinusoidal transfer function. How will you get sinusoidal transfer function? Once you are given a transfer function, you simply replace s with j omega. So now you will get gj omega. So now you can calculate what will be the magnitude and what will be the corresponding phase angle. Okay, and hence you can find what will be the frequency response. Okay, so this is the, now here we have considered the output magnitude and output phase angle. You can see here it is a function of frequency, right? For say omega equal to 1, then you have a particular magnitude and some phase angle. Omega equal to 2, another magnitude, another phase angle, and so on. So it is a function of frequency omega. Both the magnitude and the phase angle is a function of frequency. Okay. Now, what are the advantages of frequency response? Advantages. Advantages of frequency response. One, in most of the communication systems, most of the signals to be processed are sinusoidal. Or composed of sinusoidal components. Hence, frequency response is of more importance. and frequency response is of more importance. Okay. Then for higher order systems, for higher order systems, it is difficult to obtain. It is difficult to obtain the time response analytically. Okay, for lower order systems, time response will be comfortable. But as the order of the system increases, it is very difficult to obtain what the time response will be. But in frequency domain approach, but in frequency domain, graphical methods exist. Graphical methods are available. That are not limited to low order systems. Okay, so suppose you have a second order, third order transfer function, then you can find what's the time response. Okay, but as the order increases, it becomes difficult to find the time response. So in such cases, we can use frequency domain approach where there are some graphical techniques like border plot, Nyquist plot, etc. Okay, so we can, with the help of those things, we can find how it behaves in the frequency domain. Okay, and third, effects of noise, disturbances, etc. Effects of noise, disturbances, etc. can be better visualized in frequency domain. What is noise? Noise is an unwanted high frequency signal. What is disturbance? Unwanted low frequency signal. So what is the impact of noise, or what is the impact of disturbance on the system can be better visualized in frequency domain. That is another advantage. And fourthly, there are correlating relations. There are correlating relations between the frequency domain and time domain performances. In a linear system. So that the time domain properties based on the time domain properties of the system, can be predicted based on frequency domain characteristics. Frequency domain characteristics. Okay, so time domain specifications and frequency domain specifications are correlated. So that means from the frequency response, we can calculate what will be the time domain specifications. Okay, it is easy to predict, right? So as I said before, time domain analysis is restricted to low order systems, but frequency domain can be applied to higher order systems because there are graphical methods which will help us to analyze the system in frequency domain. So once you know the frequency domain specifications, you can calculate what will be the time domain specifications. Okay, so these are the few advantages of frequency response, right? Now, next heading, frequency response of closed loop system. Frequency response of closed loop system. Okay, suppose you have a feedback system like this. G of S, this is a negative feedback. This is R of S, input signal. C of S is the output signal. Feedback path transfer function is H of S, like this. Okay, so what will be the closed loop transfer function? C of S by R of S. Okay, closed loop transfer function. Closed loop transfer function. Okay, I will indicate that with M of S. What is that? C of S divided by R of S. And we know it will be nothing but G of S divided by 1 plus G of S H of S. Okay, so we are going to obtain frequency response. We want to obtain the frequency response. So what's the next step? We have to obtain the corresponding sinusoidal transfer function. Sinusoidal transfer function means you replace S with j omega in the transfer function, and the resultant thing will be the sinusoidal transfer function. So I will get M of j omega as C of j omega divided by R of j omega. Okay, and that will be nothing but G of j omega divided by 1 plus G of j omega into H of j omega. Okay, now M of j omega is a complex quantity having magnitude and phase angle. So what will be the magnitude of M of j omega? Magnitude will be mod Gj omega divided by 1 plus Gj omega Hj omega. Okay, or I can apply the modes separately to both numerator and denominator. Okay, Gj omega divided by modulus of 1 plus Gj omega Hj omega. Okay, and what will be the angle of M of j omega? Angle of Gj omega minus angle of 1 plus Gj omega Hj omega. It is something like A angle alpha by B angle beta. Okay, it is A by B angle alpha minus beta. So I can write this as angle of Gj omega minus angle of 1 plus Gj omega Hj omega. Okay, so this will give you the magnitude of the closed loop transfer function. This gives you the phase angle of the closed loop transfer function. Okay, now most of the control systems exhibit low pass filter characteristics. What do you mean by low pass filter characteristics? That means all frequency signals below the cutoff frequency will be passed, and all frequencies above the cutoff frequency will be attenuated. Okay, or ideally, it has a characteristics like this. Omega. Okay, this is 1, and this is the magnitude mod modulus of MGMA. Okay, so this is called the cutoff frequency. So all signals up to frequency omega will be passed through the filter, and afterwards all this higher order frequencies will be attenuated. Okay, and how will be its phase angle? there will be a delay. Okay, the filter has a delay, and that delay will be reflecting in the phase angle part. Okay, so I mark this as angle m of j omega. That will be a straight line like this. Okay, so these are 0. Okay, so this is the gain phase characteristics for gain phase characteristics for an ideal low pass filter. Okay, so we prefer to have this kind of response, but it is not possible practically. So if had this been realizable, then this would have been the most apt control system that would have been available to us. Okay, because up to corner frequency 1, the output will be transmitted. Okay, output and input will be in phase, and then afterwards higher frequency signals will be attenuated. Right, this is what we prefer, but this is physically unrealizable. This is an ideal case, ideal situation. Okay, but practically what happens? Practically, what happens is that it will start like this. There will be a peak, and then gradually it will be attenuated. Okay, practical control systems have a response of this kind. This is the magnitude, mode mg omega. Okay, so suppose this starts from 1, then there will be a peak here that happens at a frequency omega r. This peak magnitude is what we mean by resonant peak mr, and this is 0.707. Okay, this much band of frequencies is called bandwidth, and slope at this at high frequency range, slope at this point at high frequencies, that is called cutoff rate. Cutoff rate. Okay, so ideally it should have transmitted up to omega c all the signals. Okay, with unity gain. That is why it is a gain of 1 here. But here what happens? Practically it will be 1 in phase for some time, and then onwards it increases in magnitude. Okay, now what will be the phase angle? Phase angle will be something similar to this. Omega angle mg omega. Okay, it will be a curve. It will be a curve like this. Okay, it starts from 0 degree. Okay, so this is how a typical. So this is the typical gain phase characteristics for a typical feedback control system. Gain phase characteristics for a typical feedback control systems. Okay, so now we are going to see a simulation, right? So I have told you that control systems have low pass filter characteristics. Okay, and I have shown you what are the typical gain phase characteristics of a control system, right? So let us see a simulation and understand what is happening. Okay, so here we have an RLC series circuit here, right? So there's a sinusoidal voltage being applied. We are measuring the output across the capacitance. Okay, so how we do this simulation normally? For that, we need to apply a sinusoidal input of varying frequency. Okay, and in practice, so frequency response can be obtained by applying a sine wave. Okay, by applying a sine wave input to the system, and we sweep the frequency from 0 to a value behind the frequency range. Okay, so the input is represented in red color, and output will be in blue color. Okay, so you can see what is happening. So the input will be a sinusoidal waveform of varying frequency. Okay, you can see what is happening here. So the input is a sinusoidal function whose frequency increases with time. Okay, and at low frequencies, both the input and the output are equal in magnitude and in phase. once the initial transient part has died out. So this corresponds to a magnitude of 1 and a phase of 0 degree on the magnitude and phase plots. You can see at intermediate frequencies, what happens? The output actually gets larger than the input. Okay, but there is a growing phase lag. Okay, so as frequency increases, what happens? As frequency increases further, the output decreases. Okay, and at higher frequencies, the input and output are completely out of phase. So in short, the magnitude plot starts at 1, then increases, followed by a decrease. Okay, so this is what is exhibited by a practical feedback control system. Okay, as you can see here. Now we will see what are frequency domain specifications. So let me draw this gain phase characteristics once again. Okay. Frequency domain specifications. Frequency domain specifications. When we discussed time response, we had discussed about some time domain specifications like rise time, peak time, and so on. Okay. So similarly, here we have what is called frequency domain specifications. Okay. So I will draw the typical gain phase characteristics once again. So this is mode mj omega. So it starts from here 1. Okay. So this is 1. This is the peak point at omega r. This is the omega axis. Then here is say 0.707. This frequency is called omega BW bandwidth. Okay. And the slope at high frequencies is called cutoff rate. Okay. Similarly, if you draw the angle characteristics, this is angle m of j omega, angle m of j omega, angle m of j omega. So it will be something like this. Right? 0. Okay. So now we will try to define some frequency domain specifications. Okay. So we will keep this figure in mind. So first one is resonant peak. Resonant peak or resonant magnitude. Okay, both are one and the same. We indicate it with the letter MR. Okay. So what is resonant peak? Resonant peak is the maximum value of the closed loop transfer function. The maximum value of the closed loop transfer function magnitude mod mg omega over the entire frequency range. It's obvious, right? So you have done what is resonance in series R circuit. What happens? Current becomes the maximum at that particular point, right? So correspondingly, we have what is called resonant peak. So resonant peak is nothing but the maximum value of the closed loop transfer function magnitude. Okay, and this corresponds to resonant peak MR corresponds to overshoot in the step response. Okay, resonant peak corresponds to overshoot in step response. Typical values are in the range from 1.2 to 1.5. Okay, that's about resonant peak. So next is resonant frequency. What is resonant frequency? Frequency at which resonant peak occurs. That is what is resonant frequency. frequency at which the resonant peak occurs. The resonant peak or resonant magnitude occurs. Okay, that is what we mean by the term resonant frequency. Now, third one is bandwidth. So what is bandwidth? Bandwidth is the frequency at which the magnitude of the closed loop transfer function is reduced to 1 by root 2 of, or 70.7% of the low frequency value. Okay, what was the low frequency value? Low frequency value or DC gain means the gain when S is equal to 0. What's the gain at S equal to 0? S tending to 0. Okay, so it is 1 basically, right? So 0.707 times that value, or 70.7% of the low frequency value. Okay, so what is that corresponding frequency at which the magnitude becomes 70.7% of the low frequency value? That is what is called bandwidth. Okay, frequency at which the mode mg omega magnitude of the closed loop transformation is reduced to 70.7% of its low frequency value. Okay, or what is 1 in decibels? 20 log 1 is 0 dB, right? 3 dB down. That's also an equivalent way of representing bandwidth. Okay, or 3 dB down, 3 decibels down from its 0 frequency value. From its 0 frequency value. That is what is called bandwidth. Okay, so one is what's its low frequency or 0 frequency value, 70.7% of that magnitude. Okay, and you draw a line, see at what magnitude point it hits, the corresponding frequency is called the bandwidth. This is the bandwidth range. Okay, this much is the bandwidth. Now, larger the bandwidth, what happens? The faster will be the rise time. Large bandwidth means faster rise time. Your response will be more fast. Okay, so smaller bandwidth, it's obvious, will result in slow and sluggish time response. Slow and sluggish time response. Slow and sluggish time response. So can we go for large bandwidth? What's the problem if we go with large bandwidth? Then noise can happen. Okay, noise is high frequency unwanted signal. Right? So if we increase the bandwidth to a larger extent, then noise can come in. Right? So that is the problem. If you decrease the bandwidth, what happens? The response will become more and more slow and sluggish. Okay, so it is a trade-off kind of thing. You have to decide which you want. Okay, it's a compromise. You have to make a compromise. Okay, that's about bandwidth. Then next, frequency domain specification is what is called gain margin. Gain margin. What is gain margin? Gain margin of an LTI system is defined as the factor by which the gain of an open loop system is to be multiplied at phase crossover frequency. Phase crossover frequency omega pc. Okay? Or the amount of gain decibels, the amount of gain in decibels to be added to the open loop gain at phase crossover frequency. At phase crossover frequency. So as to bring the closed loop system to the verge of instability. Okay, so physically it means how much gain you can add to an open loop system before the system is brought to the verge of instability. That's a physical mean. Okay, so in the coming classes we will see what is border plot and what's Nyquist plot. Then only you will understand this definition in more depth. Okay, so I suggest you that you hold up to that. Okay, up to the point where we take up border plot as well as the Nyquist plot. Okay, so gain margin can be found mathematically like this. Gain margin is 1 divided by mod Gj omega Pc Hj omega Pc. Okay, this is in absolute magnitude, or in decibels it will become minus 20 log 10 mod Gj omega Pc Hj omega Pc decibels. Okay, so what is phase crossover frequency? So we have seen that magnitude is a function of frequency, and close to phase angle is also a function of frequency. Okay, magnitude is a function of frequency, and phase angle is also a function of frequency. Fine. So at a particular value of frequency, right, the gain or the magnitude becomes equal to 1 or 0 dB. Okay, that particular value at which the gain becomes equal to 0 dB or 1 is what we call gain crossover frequency. And at some value of frequency omega pc, the angle of the transformation can become angle part will become equal to 180 degree. That is what is called phase crossover frequency. So omega pc is the frequency at which angle g omega becomes equal to 180 plus or minus 180 degree, and omega gc or gain crossover frequency is the frequency at which the dB gain becomes equal to 0, or in absolute scale gain is equal to 1. So gain margin is calculated at phase crossover frequency. That's the point here. Okay. So when we discuss border plot and Nyquist plot, it will be more clear. So let me come to the next point. Next one is phase margin. Phase margin. Okay. Phase margin of an LTI system is its additional phase lag is the additional phase lag phase lag means what? Negative. Okay, it's a negative phase to be added. To be added at gain crossover frequency. Gain crossover frequency omega gc to the open loop system. To the open loop system, so as to bring the closed loop system to the verge of instability. Okay, so how much phase angle, how much negative phase angle you can add to a system, okay, to an operative system before the closed loop system is brought to the verge of instability. That is what we mean by phase margin. So that is given by 180 degree plus angle Gj omega Gc at J omega. So why are we doing all these things? In time domain, it was easy to check whether a system is stable or not. We have to check for the output response. If we had a plot, from the plot we could say if it is converging to a finite value, okay, it was stable. If it is diverging, okay, it was unstable. But how will we say whether a system is stable or not in frequency domain? For that, we are given these figures of merit, gain margin and phase margin. A system is said to be stable, or for a stable system, both the gain margin and the phase margin must be positive. Okay, if either gain margin is positive or phase margin, if either gain margin is negative or phase margin is negative or both are negative, the system is said to be unstable. So here, when we say gain margin must be positive, we mean gain margin in decibels. Okay, decibel gain, right? That's the mean. Okay, so for a stable system, both the gain margin and the phase margin has to be stable. So we will stop here for the day. Okay, thank you.